and we're going to talk about solutions. So think about a glass of water at home, and you take a teaspoon of salt and you dump it in the water with a spoon, and then you stir it up. I think we all know or can predict what is going to happen, right? The salt dissolves in the water. It looks like it disappeared. But if you taste the water, is it still there? Oh yeah, salty water does not taste good. So the salt has mixed with the water, and it now looks like it is one substance, right? And so we call this a mixture, and it's a homogeneous mixture because it's uniform throughout. The water at the top is salty, and the water at the bottom is just as salty. We can prove, besides tasting it, that the water is still there by heating that solution and boiling the water away. And when we get all the water to boil off, the salt will still be there. It might not be in nice little square crystals like it was before, but it's still salt. So we have another word for homogeneous mixtures. We call them solutions. So a solution is a homogeneous mixture. And there are two parts to a solution because you have to have at least two things that are mixed, right? So we have the solvent and the solute. So the solvent, sometimes a little hard to define, but generally the solvent is the one that there's more of. So if we're putting a little bit of salt into a glass of water, there's more water. So we call that the solvent. Another way to tell is that the solvent retains its physical state. So when we mix the salt with the water, the salt started out as a solid, the water started out as a liquid. When we mix them together, is it a solid or a liquid? It's a liquid now. The water kept its state, that's the solvent. So the other thing is the solute. So there's less of the solute. Sometimes the solute changes its state. In this example, the salt went from a solid to becoming part of this liquid mixture. You can have more than one solute. What if I took a teaspoon of sugar and put it in the water and stirred it up? The sugar would dissolve, right? And now I've got a solution containing two solutes, sugar and salt, dissolved in water. Any questions? So solutions are mixtures, and with a mixture, the composition can vary. I could put 2 teaspoons of salt in the water or 1 teaspoon. It's still salt water, but it's not exactly the same. A pure substance has a constant composition. So in water, we always have the same ratio of hydrogen to oxygen because it comes down to the individual particles all being the same. So in order to describe a solution, we need to do more than just say what the parts are. We need to say how much of each is in there. And so we call that a concentration. We have quantitative ways of describing this and qualitative. So qualitative does not involve numbers. Qualitative would be a dilute solution or a concentrated solution. Those are relative terms, right? Dilute means there's a relatively small amount of solute. A concentrated solution has a large amount of solute in the solvent. So here we've got the concentrated solution versus the dilute. You make the dilute solution by adding more of the solvent. So this is somewhat like concentrated frozen orange juice, right? There's a lot of orange stuff in there and not very much water. And to make it drinkable, you're going to add water and make it more dilute. I grew up in the Midwest, and frozen concentrated orange juice was really the only kind we ever got. And now I live in Reedley where there's oranges all over the place, and I wouldn't drink that stuff for anything. Fresh squeezed, it's the way to go. Okay, so quantitative descriptions, solution concentrations. The one that chemists use the most is called molarity. And, you know, if you just rearrange the letters, you'd get morality, but it has nothing to do with that. It's molarity. It's abbreviated with a capital M, which is a very nice, convenient, short abbreviation, but also causes a fair amount of confusion for students. Molarity is defined as the amount of the solute measured in moles divided by the volume of the entire solution measured in liters. And so these units have to be used, moles of solute and liters of solution. So molarity is moles per liter. So when you see that capital M, that means moles per liter. It's not an abbreviation for mole. It means moles divided by liters. And we have to be careful that this is clearly a capital M, because if I make my M like that, is that a capital M or a lowercase m? Is that molarity or meters? It depends on the relative size of the other letters. 2 molar or 2 meters, they can look a lot alike. So you can make your M's very pointy, or what I typically do, because I'm in a hurry, I underline the capital M. You don't have to do that, but I'm just telling you that that's how I write it most of the time. So molarity, moles of solute per liter of solution. So here's an illustration of how you would make a solution with a particular concentration. Here we're trying to make a 1 molar sodium chloride solution. So that 1 molar means 1 mole per liter. So we're going to take a volumetric flask here. This is a special kind of glassware that will hold precisely a specific amount of liquid. And so this is a 1 liter flask. And we're going to add 1 mole of sodium chloride. And we're going to have to do a calculation there to find out what mass to weigh out. So 58.44 grams of sodium chloride. We're going to add that to our flask. And then we're going to add our solvent and add some water. Because of the shape of this flask, you don't want to fill it all the way up right away, because it becomes very difficult to mix. So you want to fill it up so it's still down in the fat part, and then you can swish it around. And you're going to mix it around until the salt's all dissolved. Then you're going to add more water. All of these volumetric flasks are going to have 1 line on the neck. The reason it has a long skinny neck is because then it's got a very small surface area, and so a little change in volume will be a big change in the height of the meniscus, so we can be more precise. So you want to add water until the bottom of the meniscus is right at that line. Then you're going to put a stopper in the top of this, and then you have to invert it and mix it. We'll be doing this on a smaller scale in, I think it's experiment 4B. We're going to make salt solutions. Okay, so let's calculate solution concentration. Calculate the molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. Well, let's take those numbers and write them down. So I've got 45.4 grams of sodium nitrate, and I've got 2.50 liters. It can just be helpful to pull the numbers out so you can get away from all the words. So that's what I'm starting with. What am I trying to calculate? Molarity, right? Calculate the molarity. So molarity requires an equation. Molarity equals moles of solute per liter of solution. So I need to know the moles of solute. The solute here is the sodium nitrate. And I need the volume of the solution in liters. Do I know either of those? Yeah, I know the volume of solution. They gave that to me, 2.50 liters of solution. But they didn't give me the solute in moles, they gave it to me in grams. And that is extremely common because that's what you get when you weigh it out. You get a mass. But in the concentration, we want moles. So there's another time where we're converting grams to moles. So I've got grams and I want moles. So I'm going to multiply by moles, divide by grams. The grams cancel. And now I just need to find the molar mass. So there is one sodium, 22.99, and I've got one nitrogen, 14.01, and 3 oxygens. $85. How many sig figs does that number have? Should have 4, right? Sometimes we get misguided and we think 85, whole number, exact number. No, that's not a counting number. The calculator says 85 because this just happened to work out to exactly 85, but there's uncertainty. So we should put zeros there to indicate 4 significant figures. So that many grams is equal to 1 mole for this compound. So I've got 1 mole of 85.00 grams down there. Take my 45.4, divide by 85, 0.534. I'm just keeping track of significant figures as I go along. This one had 3, so this result should have 3. And then I'm going to write down 2 extras because that's what I do. That many moles of sodium nitrate. If that was going to be a final answer, I'd round it off. But it's not. I'm going to use that in a calculation, so I'm going to bring those 2 extra digits along. We don't have to write down all the digits, just 2 extras. So I'll bring this in here, 0.534, underlining that to remind myself. Moles. So we got 0.53411 divided by 2.5. And this result should also have 3 significant figures. But again, I'm going to write down 2 extras. And this is going to be my final answer, so I'm going to round this. I'm going to get 0.214. The units are moles over liters. Or you can call this 0.214 capital M. Any questions? You may have noticed in lab when we were using solutions that some of the bottles had things like 12M or 0.1 M. That's telling the concentration of the solution. Chemists like molarity because when we're talking about chemical reactions, we need to think in terms of moles of things, right? When we do stoichiometry, we end up with this mole-to-mole thing in the middle because that's what we get from the chemical equation. The nice thing about molarity is once we've got that solution and we know the molarity, we can measure out a certain number of moles just by using the volume. So molarity is a conversion factor going between moles and liters. So this is just showing us an example of a 0.5 mole per liter or 0.5 molar sodium chloride solution. We can use this to convert from liters of solution to moles of sodium chloride. If we tip this upside down, we can use it to convert from moles of sodium chloride to liters of solution. So it works just like the molar mass does, Molar mass converts between grams and moles. Molarity converts between moles and liters. So how many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? So again, let's pull the numbers out. We got 1.55 liters, and I've got 0.758 capital M. The capital M is very concise when you're typing, but it's easy to get confused about what it means when you're writing with your hand. So instead of writing the capital M, write what it means. This is 0.758 moles divided by liters. Just an abbreviation for that. When I write it out this way, my brain says, oh, that might be a conversion factor. When I look at this one, I'm like, yeah, just capital M's, big M's, what are those? So those are my numbers. Pull those out, and then what's the question? How many grams? So I'm trying to find grams of sucrose. They gave me the formula because we don't expect you to know that. And I've got these two numbers to start with. These sorts of calculations, we don't use the equation, we just use dimensional analysis. The molarity is the conversion factor. So I want to start with this volume, and I'm going to use this as a conversion factor. Sometimes students are trying to start with this one, and you might be able to get there fine, but when I look at this, I see moles per liters. That's got a per in it, right? So that's my conversion factor. This one's just liters. That's not going to help me convert between anything. So my path is I'm starting with liters, and the molarity allows me to convert to moles, and then I can find the molar mass and convert from moles to grams. So we're just putting together individual pieces that we've learned. So I've got liters, I'm going to go to moles, and then I'm going to go to grams. I'm going to put moles down here, so those cancel, and liters down here, those cancel. Moles per liter, this is the molarity. The number goes with moles, and liter is by itself. So 0.758 moles per liter. That's a conversion factor we can use for this problem. And then I need the molar mass. So 12 carbons, 22 hydrogens, and 11 oxygens. $342.296. Those are all the digits that my calculator gave me. It's only really got 4 sig figs, but those 2 extras are kind of nice to hang around. So 1 mole of this compound weighs 342.296 grams. So now I have all my numbers in place. Start at the beginning, 1.55 times 0.758 times 342.29 equals. My starting number had 3 sig figs, and nothing in the middle had less than that, so I still have 3 significant figures here. And I'm going to round that to 402 grams. It's possible to do this without writing anything down. And there are times when you're just trying to do a quick and dirty calculation that you might want to do that. But if you're doing anything where it matters that the answer is correct, you need to be able to write this down. You don't necessarily have to write that out. You don't necessarily have to write the path out, but you need to be able to just write this line right here.